So welcome to Types 3, and just as the AV switches over, the first talk will be given by Lionel Parreaux, and the title is When Subtyping Constraints Liberate, a Novel Type Inference Approach for First-Class Polymorphism.
All right. Hello, everyone. Welcome to my talk on subtyping constraints Liberate. So let's first talk about polymorphism, and in particular, the classical pre-next polymorphism of ML and how it compares to first-class polymorphism. So you all know what's the type of the identity function, right? Whoops. Okay, so this function has a polymorphic type, right? For all A to A, and this means you can use it in several positions which expect different types, and every time you use it, you're free to substitute the type variable A with whatever is required at the call site. Okay? And now, how about this term, which puts the id function inside a singleton list constructor? So what ML says is that this has type for A, a list of A to A, but we can also make it list of for A to A, which requires more advanced type system than ML, but is also more precise because the type of this list is the type of list that contains polymorphic functions, right? Whereas the elements of the list in the other type are monomorphic. So in order to achieve this other type that I showed, we need to be able to substitute type variables with polymorphic types. So the singleton list constructor has type for A to list of A, and we want to instantiate it by substituting A with for A to A. So I should have picked another variable name, but this is not the same A, right? And when you apply it to the identity function, then you get list of for A to A. Okay, well, why do we want to do these kind of things? It seems a bit not very useful, but actually there are many applications of such type systems with data structure fusion, encapsulation, existential types, etc., etc. And more importantly, we need the full power of first-class polymorphism to be able to abstract over all of these use cases. And these things are actually pervasively done throughout the Haskell ecosystem. So it's a quite important thing that we want to have. So what's the type of the following function bar, which takes two parameters. It tests whether the first parameter is true, in which case it returns its second parameter, otherwise it returns it. And it seems we have to choose between two types. The first type is a type where the quantification appears on the outside, where you instantiate the type of id here. And so you get the for A on the outside of the function type. So this is the type that ML will tell you. And with first-class polymorphism, we also have other types that are possible. And so in this case, we can also say that this is a function that takes bool and returns and a polymorphic function and returns a polymorphic function. And so neither type is more general. You can see that using bar with these two examples works only with one of the other type. Okay, so we're kind of stuck because we don't know which type to pick, right? We don't know when to generalize and when to instantiate type variables. And so let's use an analogy to explain what's happening. So you're probably familiar with finding the roots of polynomials. And here's an example polynomial. And you probably know that we can solve these polynomials in the real and imaginary domains. But when you solve it in integer domain, it becomes very awkward, right? Because you have to make discrete choices. Integers are much less fluid than real and imaginary numbers. So using imaginary numbers, you can have one solution, and these numbers are much more fluid and they smooth over the rough edges of integers, right? So the question is, what are the imaginary numbers of type inference? And I argue that subtyping plays this role. Okay, so let's look into subtyping with first-class polymorphism. And You may have bad memories of subtyping from university, where they teach what I like to call AKOP, or Animal Kingdom-oriented programming, right? But that's not the only thing you can do with subtyping. So I hope that by now, thanks to the other talks, you're convinced that subtyping is more than that. And in particular, in the context of a first-class polymorphism, you have a natural subtyping order between polymorphic types. So for example, the polymorphic identity type for A to A is a subtype of int to int because it can be instantiated to int to int, okay? And you can enrich this subtyping relationship with more rules such as distributivity, which allow you to close typing under eta conversion. So here's an example where we can we add a subtyping rule to distribute the outer quantification inside the inner function type. Okay. And so basically, what I'm trying to say is that subtyping makes sense for a first-class polymorphism, and it allows some flexibility. It allows an expression to have more than one type and no longer be limited to one type. And as the example, let's go back to bar. So the function bar we saw before can actually, we can actually give it a type that uses subtyping. So in this case, we use the least upper bound of the subtyping relationship, which I denote using this union symbol, right? And it turns out this is the principal type of the bar function. So bar is now a function that for all A takes an A and returns either A or the polymorphic function identity function type, okay? And so it turns out we can simplify this type to something that's a bit less ugly, but this is another topic. So this allows to call both bar of true and sucks and 0, which gives you an int on the output, and bar of true of id, which gives you a polymorphic function type as the output. And it's not surprising because, as I said, this is a principal type. So you no longer need to make premature polymorphism decisions, such as do we need to instantiate, do we need to generalize when you have subtyping, because you can basically encode the control flow of the program using subtyping. So let's talk about type inference using this subtyping relationship. And type inference isn't that hard, right? Source? Well, done right. A compiler should be able to figure out types automatically. It's not that hard, right? So let's see, what are the actual challenges that you have when you try to do this? Consider the following function. Foo of f makes a tuple of f of 1, 2, 3 and f of hello, so it applies its argument function to two incompatible types, and this is not typeable in ML. But with first-class polymorphism, it becomes typeable, and here's an example of a type you can give to foo. It's a very specific type, right? Here we decided arbitrarily that the function will return an option of the input, okay? And so this means that if you're able to infer these kind of things, this should work. You should be able to define foo and then use it in your program with functions such as fun of x to sum of x, because foo can be typed using this compatible function type, okay? And so how do we achieve this? How do we find a type that's good in general, instead of specifically picking one particular possible type? So this is a hard problem. Simon Pittenjohn himself, one of the most important person in this field, said that he tried to solve this for 15 years, and at the end ended up with a system that still rejects this program. And he also mentions MLF, which is the undefeated champion in first-class polymorphism type inference so far. But even MLF fails to type check this example. It's a bit unsatisfactory, right? Because this is just an abstraction of the example using the identity function that I showed at the beginning. So the problem is that we're looking at this type, and we see that the function is applied to two incompatible types. So intuitively, we are like, okay, so the function should be polymorphic, right? So it should be for A to something else. But what is this something else? It could be many things. It could be for A to A, A to int, A to list of A, etc., etc. And so our approach, which is done in SuperF, a new type inference system using subtyping, is to infer an intersection type, right? So here we are using the same function in two different positions, and that gives rise to an intersection. So the function type, the type of the argument function is now required to be both a function that takes ints to some a and strings to some b and returns a tuple of a and b. And this, again, is the principal type of this function. We can actually demonstrate it. And so this way you can call foo with all sorts of functions that return different things and get the expected type, right? So foo of the identity gives you int and string, and foo of the sum constructor gives you option of int and option of string. What are intersection types? Intuitively, you can think of parametric polymorphic types, such as for A to A, as an infinite intersection of all the possible instantiations of this type, right? So in this context, it's clear that assigning to the f parameter of foo an infinite intersection type is overkill, right? Because actually it applies its argument to two specific types. It doesn't need to have this full infinite type. And so that's why we can use this type in this case. Okay, but I've actually lied a bit because the core language of SuperF does not use unions and intersection types. These are actually syntax sugar that are presented to users because they are intuitive and nice to read. But actually, what we use is called multi-bounded polymorphism. And so it means that polymorphic types include a set of bounds. So a bound can be an upper bound on some type variable alpha or a lower bound on alpha. And so this signature that uses an intersection type is actually the same as the following signature that uses an additional type variable C with two upper bounds, one from int to A and one from string to B. And similarly, the union type we saw before is actually equivalent to a type that quantifies over some extra variable B with two lower bounds. So this precisely encodes unions and intersections when they are restricted to positive and negative positions. And so basically this follows the idea of algebraic subtyping, which we reformulated in terms of upper bounds and lower bounds in previous work. Okay, so what are the challenges of implementing SuperF? There are many challenges. There are some risk of non-termination if you solve constraints in a naive way. And there's a risk of polymorphism extrusion. It's not clear how to do type check annotations. So actually, I don't have time to explain how all of these are solved. So look at the paper if you're interested. And first, let's talk about the limitations of SuperF, which is very important to talk about. Because no matter how you slice it, type inference for first-class polymorphism is undecidable. Most problems are undecidable. And so it should be expected that we have to make some concessions. And the concession we make in the case of SuperF is that there's a heuristic for termination, which looks at the subtyping constraints that are being solved at the current point. And if it sees something that looks recursive, it just aborts constraint solving, and type checking fails. So this happens for the big omega combinator that you see here. It's an infinite loop, and it actually makes type checking infinitely loop, right? Because type checking in this case stays very close to the term and ends up basically simulating the term. So this doesn't actually trigger in practice very often, as long as you type recursive functions monomorphically. So you can type most ML programs. We actually conjecture that all ML programs are typable in SuperF. And so it does make type checking incomplete theoretically, right? And the other restriction is on the syntax of type annotations. So the users can write type annotations in their programs, but it's very hard to check these annotations if they use bounds. And so we restrict the syntax of type annotations to SystemF types, so that users cannot use actual bounds in their type annotations. And we argue that this is fine because functional programmers don't actually care that much about bounds in their polymorphic types. In Haskell, for example, there's no bounds, but there are many uses of first-class polymorphism. And you can intuitively think that SystemF types with subtyping are like real numbers. And you need a bit more flexibility to infer types. So SuperF types with bounds are like imaginary numbers. And so they are non-denotable types that are here just for type inference. But at the end of the day, what you care about and what you end up with and what you use in type annotations are SystemF types. Okay? So the SuperF is implemented in an existing programming language, and it's evaluated on many test suites that we extended. And for example, we also ported the OCaml list module. And it turns out that SuperF can handle, without any type annotation, all of the examples that were previously considered in the literature. So if you look at the blue columns here, SuperF has all the black circles, which means it type checks the programs without any problem. And so this is the first. Actually, the examples are too trivial, so we made the examples a bit more complicated. We added more complicated examples, and to better exhibit the limitations of SuperF, but SuperF still does better than other approaches. Okay, I don't have time to talk about the soundness of SuperF. It's based on the soundness of system FCC by Cretin and Rémy from 2014. And yeah, let's keep this. Well, I don't have time for future works either, but my conclusion is that unification is dead. Long live subtyping. Okay, and the end. Thanks for listening.
Thank you, Lionel. So we have time for questions.
Hi, thanks for a really nice talk. I'm wondering if there are situations where your constraints solving would loop, but somehow, but otherwise make something which you would consider to be progress, and whether, if that's the case, you could leverage some techniques from, say, the size change termination world or checking infinite descent in cyclic proofs to kind of work out when this is the case and so know when you could have a solution in those situations, as opposed to situations which are just true looping, like the omega situation you showed.
Right. I think that's correct. You could refine the heuristic to include some more advanced heuristics to determine whether the thing will eventually terminate or not. Because currently we abort constraint solving as soon as you have something that looks recursive, right? So we could refine this using the usual termination heuristics. And we could. There are also other things we could do. For example, we could, instead of aborting constraint solving, we could undo polymorphism decisions that were made earlier, and that would allow to type check the big omega combinator. So that's yet another approach you could take to make things better. Or you could move to impredicative version of SuperF, which would probably give you completeness.
All right, thank you.
Hi, nice talk, thank you. So when we're programming, we do more than just type in code and watch it run. We have to interact with it. There's documentation systems that get generated. There's, you can query the type of something in some interactive system.
Right.
Have you thought about how these types might get presented to users, especially if they can't write them?
Yeah, that's a good question. So these bounds that we infer are actually a reflection of the control flow of the program. And we do generate type errors that understand this data flow of the types and explain things not in terms of bounded types, but in terms of which piece of type flows in which other position. There's a web demo that you can try that shows the system, and you can see that it gives good errors usually. So, for example, maybe if you write something like this, it will give you an error that traces the flow of the value and tells you exactly what failed during type inference. Mm-hmm.
That looks very cool. Thanks.
Thanks.
I'm willing to live without bounds, but I really like my intersections and unions. So,
right.
Can we extend this to algebraic subtyping, which has intersections and unions?
So the original algebraic subtyping doesn't really have intersections and unions any more than this system. It's just data flow types, basically. We did extend algebraic subtyping with proper first-class unions and intersections in a previous work, which is implemented in ML script. So you can actually do this in ML script. You do have access to unions and intersections, although you cannot use intersections to implement things like overloading, because that would be a bit too hard to do constraint solving and too expensive.
Mm-hmm. Thank you.
We also have a question on Discord. Your bounded polymorphism examples had only upper bounds on a variable or only lower bounds. How do you present them to the users when a variable has both upper and lower bounds?
So actually, what we present to users is usually unions and intersection types. So we don't actually present bounded types to users unless the type is recursive, in which case we will just write for all A and then list the bounds of A. So A is less than something and greater than something else. We just list the bounds, right?
Okay, could we get the AV for the next one ready while we take one more question?
Hi, so one thing you didn't talk about is like the algorithmic complexity of this kind of type checking. And like, I mean, what I remember from the works in the 90s about inference with subtype bounds, they tend to explode. So what's happening here?
Yeah, that's a good question. I don't have a very good answer to it. It's probably expensive. So the basic system, algebraic subtyping, is cubic, not considering checking things against the signature, which is actually exponential. Since our type inference approach checks, it essentially has to include checking things against their signature because of first-class polymorphism. So it's for sure exponential to infer things in the general case. In practice, it's not that bad. If you restrict yourself to normal ML-style data types, as you can see in the web demo, you can experiment with it and see that it's actually very fast to update the results, right?
Okay, thank you.
Thanks. That's all we have time for on that one. So we could thank Lionel again, please.